Good morning, students. I am B. Kavita, Assistant Professor in Physics. Today we discuss third unit in Engineering Physics. In third unit we have two lessons, dielectric materials and magnetic materials. First we discuss dielectric materials. First, what are the dielectric materials? Dielectrics are insulating materials, so there are no free charge carriers in them. Those are insulators, that's why there is no free charge carriers in them. In dielectrics, all the electrons are bound to their parent molecule. Even with normal voltage or thermal energy, electrons are not released. Even with normal voltage or thermal energy, electrons are not released. Dielectrics are non-metallic materials of high specific resistance and have negative temperature coefficient of resistance. Dielectrics have permanent electric dipole moment. Dielectrics are mainly used to store electrical energy. Examples of dielectrics are rubber, glass, plastic and mica. When dielectrics is placed in an electric field, then separation of positive and negative charges takes place, causing polarization of the dielectric. When dielectric is placed in an electric field, you put the dielectric material in electric field, the charges are separated. The charges are positive and negative charge. Those two charges are separated. That is called the polarization. The dielectrics are of two types, polar dielectric materials, non-polar dielectric materials. In this diagram, we see polar molecules and non-polar molecules. In polar molecules, already exist of dipole moments, dipoles, here plus positive charge and negative charge. They maintain the dipole moment, but in non-polar molecules, there is no dipole moment in between these two charges. First, we go to polar dielectric materials. In non-polar dielectric materials, the molecules are usually diatomic and composed of same type of atoms. In non-polar dielectric materials, the molecules are usually diatomic and composed of same type of atoms. In case of non-polar dielectrics, the centers of both positive as well as negative charges coincide. Dipole moment of each molecule in non-polar system is zero. All those molecules which belong to this category are symmetric in nature. All those molecules which belong to this category, that means in non-polar dielectrics, are symmetric in nature. Examples of non-polar dielectrics are H2, N2, O2, CCH6, CH4. Polar dielectric molecules are normally composed of two or more different types of atoms. Polar dielectrics are those in which the possibility of center coincide of the positive as well as negative charges is almost zero. That is, they don't coincide with each other. They don't coincide with each other. The reason behind this is their shape. They all are of asymmetric shape, but polar molecules, non-polar dielectric materials are symmetric, but polar dielectric materials are asymmetric in shape. Example of the polar dielectrics is NH3, HCl, CH3Cl, H2O, etc. Some basic definitions in dielectric materials. First with dipole. What is the dipole? A system consisting of two equal and opposite charges separated by a small distance. A system consisting of two equal and opposite charges separated by a small distance. Those are the dipoles. Dipole moment. It is measure of the polarity of the system. It is the dipole moment means it is a measure of the polarity of the system. It is find the product of one of the charge and the distance between two charges is called dipole moment. How we can take dipole moment? The product of one of the charge and distance between two charges is called the dipole moment. Dipole moment mu is equal to Q into D. Here Q is the charge of the one of the dipole and D is the distance between two dipoles. So the product of those two gives the dipole moment. Units for dipole moment is coulomb meter. See here, these two are the dipoles. The distance between two poles is d. The product of one of the charge and the distance d is give the dipole moment. Next, electric polarization. The process of producing electric dipoles by an electric field is called polarization in dielectrics. Polarization means the process of producing the dipoles in an electric field. Polarizability. The induced dipole moment per unit electric field is called polarizability. Polarizability means induced dipole moment per unit electric field. So always the dipole moment is directly proportional to the intensity of the electric field. So mu proportional to E, mu is equal to alpha E. Alpha is the polarizability constant. Permittivity. Permittivity is a quantity which represents the dielectric property of a medium. Permittivity represents the dielectric property of a medium. It indicates the easily polarizable nature of the dielectric material. Permittivity indicates the easily polarizable nature of dielectric material. Units for permittivity is farad per meter. Free space permittivity. It represents the capability of a vacuum to permit electric fields. It represents the capability of a vacuum to permit electric fields. It is also connected to the energy stored within an electric field and capacitance. Epsilon naught, free space permittivity epsilon naught. Epsilon naught is equal to 8.85 into 10 power minus 12 farad per meter. Another definition, relative permittivity or dielectric constant. Dielectric constant epsilon r. The dielectric constant is the ratio between the permittivity of the medium to the free space permittivity. So, dielectric constant epsilon r is equal to epsilon by epsilon naught. The characteristics of dielectric material are determined by the dielectric constant and it has no units. Characteristics of dielectric material determined by the dielectric constant. Polarization vector. The dipole moment per unit volume of the dielectric material is called the polarization vector. P is equal to n mu. The dipole moment per unit volume of the dielectric material is called polarization vector. P is equal to n mu. Another definition, electric flux density. Electric flux density is the amount of flux passing through a defined area that is perpendicular to the direction of the flux. Electric flux density is the amount of flux passing through the defined area that is perpendicular to the direction of the flux. Units is coulomb per meter square. Electric flux density D is equal to epsilon naught E. And also in media, electric flux density D is equal to epsilon E. D is equal to epsilon naught E and D is equal to epsilon E. Suppose you take the dielectric material as compared to free space, if D is equal to epsilon naught E plus P. D is equal to epsilon naught E. D is equal to epsilon E. D is equal to epsilon naught E plus P. As the polarization measures the additional flux density arising from the presence of material as compared to free space. We compare to material as to free space. The flux density D is equal to epsilon naught E plus P. So here equating 2 and 3. Epsilon E is equal to epsilon naught E plus P. P is equal to epsilon minus epsilon naught E. Here we take in place of epsilon naught into epsilon R from dielectric constant. Dielectric constant epsilon R is equal to epsilon by epsilon naught. So in place of epsilon naught, we write epsilon naught epsilon R. So P is equal to epsilon naught epsilon R minus epsilon naught E into E. Here we common the term epsilon naught epsilon r minus 1 into E. Next, electrical susceptibility. Electrical susceptibility indicates the degree of polarization of dielectric material. The degree of polarization of dielectric material in response to an applied electric field. So, chi is equal to P by E, chi is equal to P by epsilon naught E and P is equal to chi epsilon naught E in place of epsilon naught. P is equal, we know this relation, P is equal to epsilon naught into epsilon r minus 1 into E. So P equating these two, chi epsilon naught E is equal to epsilon naught epsilon R minus 1 into E. Chi is equal to epsilon R minus 1. This is the relation between dielectric constant and electric susceptibility. This is the relation between dielectric constant epsilon R and electric susceptibility.